Well, hi again, everybody. Well, I've got a lot of questions on that last video I did where I showed how to add a second hard drive to my main editing workstation and enabling RAID 0 on it. And primarily those questions related to how RAID is supposed to work. So what I decided to do based upon those questions is create this video. And in this video, I'm going to go through a presentation going over the details of how RAID works to help anybody who has a personal computer. Now, I'm going to talk about a lot of history related to that, but I think the history helps. So we'll see how it goes. Once again, if you see anything here that you like or find helpful, subscribing would really be helpful. This discussion is on RAID, which can be said in two different ways. There's two different definitions for what the acronym means. One is redundant array of inexpensive disk or drives, and the other one is redundant array of independent disk. I think the second one is probably more accurate, but it's hard to tell. There's both documented. So let's start off talking about what is RAID. Well, the most common configurations of RAID, and there are a number of them, include obviously not using RAID, which defaults to the average system, even if the system includes, let's say, a BIOS capability to do so, or even if the system comes with a hardware card, and some might. Some of the server type systems do. Then you have RAID 0. Now RAID 0 is what I showed in my last video, and that's where you put two or more drives together and you stripe them so that the blocks defined by the block size when you set up the RAID alternates between one drive and the next, or if there's more than two, amongst the three, and then rolls back around again, sort of a round robin way to the first one again. And that allows you to extend the actual drive size as far as the operating system sees it anyway, and with the different SATA ports, as we talked about, improve its performance as well. Then there's RAID 5. Now RAID 5, you will see something that is a variation of RAID 5 on my new server if you go back to those videos. And what that really is when you have anywhere that's, you got to have at least 3 drives, and usually at 6 is the upper limit, although you can put more, but it becomes very inefficient past about 6. And what it does is it does striping, just like in RAID 0, but it also does error correcting parity on all the blocks. So it simulates sort of doing a drive 1, at least partially, and it uses a lot less space to do that than a RAID 1 would use. Disk space, that is. Now with RAID 5, in addition to that, it also allows one whole drive to drop out, and then it's able to correct for that with that parity. Now RAID 6 is very similar to RAID 5, but it allows for double ECC parity, which means that it's doubled along all the drives, and as a result, it eats up 2 drives rather than the one that RAID 5 would eat up. But it can also recover from more than the one. RAID 5 can only recover from 1. RAID 6 can recover from 2. Now some of the lesser common configurations of RAID include a RAID 2, which is very similar to RAID 1, but uses what's called a bit level striping. Now, in order to do its error correcting, it uses something called Hamming code, which was originally designed for memory systems, not disk systems. It is very fast and requires special hardware to do it. That's why RAID 2 normally requires a special RAID controller to be done correctly. In addition, all the disks must have their spindle speeds synchronized for that to work. RAID 3 is very similar to RAID 1 as well, but it does it at the byte level, and as a result it can do the ECC parity on small blocks rather than an individual bit level. And as a result of that, it is also very fast and requires special hardware, but also requires that the actual spindle speeds are synchronized. Again, special hardware is needed for that one. RAID 4, similar to RAID 3, but uses a full block level with ECC parity, which is very similar to a combination of RAID 0 and RAID 6. But let's just say that it actually produces a very fast RAID, but also requires a special RAID controller. RAID 7 is a variation of RAID 3 and RAID 4 combined. It takes the best of both worlds, and it also has something called caching. So on the dedicated hardware controller for it, you have to have some caching memory that actually caches in blocks from the disk. Very fast, and as a result also requires a special hardware controller. All of these generally require a special hardware controller, and you really won't find them commercially available. They were made by certain vendors in proprietary systems. Now there's also some of these nested or hybrid configurations, and one is used by a lot of implementation, and that is RAID 10, which can actually be viewed as striping and mirroring together. So RAID 0 and RAID 1, a combination of both. And I'll show you the layout of that in a little bit. RAID 50 is in a similar vein to RAID 10, but instead of being a combination of RAID 0 and RAID 1, which by the way is how it got the designation 10, it means RAID 1 plus RAID 0, but they leave out the plus. Well, RAID 50 is RAID 5 plus RAID 0. And it actually is a combination of RAID 0, as the name implies, and RAID 5. Now let's talk about the configurations. Well, let's look at RAID 0 first, which is what we showed in the last video, or disk striping. In this example, we have two 1 terabyte drives. Well, each one, for purposes of illustration, are broken into 4 blocks. So as you can see, each drive has unique data on it. Drive 1 has blocks 0 through 3, and drive 2 has blocks 4 through 7 because they're butted together and become one logical drive. However, they have separate interfaces to the SATA controller, and that's where you pick up the extra performance. So this thing will actually go at about 1.9 times the speed of just a single drive using a single SATA controller. Now RAID 1, full disk mirroring, they have 2 drives for every one. So in this example, we have disk drive 1, which is 1 terabyte, as well as disk drive 2, 1 terabyte. And each one has only 4 blocks on it for the 1 terabyte. Each one has a block 0 through 3 because they are mirrored. You see the little mirror I put there in the middle of the thick orange arrow? That's what that's supposed to represent. But the resulting of this is you only really get 1 terabyte of storage, whereas in the case of the striping, we got, as you can see there below the sign, we actually got 2 terabytes. So this one we only get 1. Now RAID 5, which is set as my new server, in this case we're using 4 drives. Now it can be anywhere from 3 to 6, but what we have here is each drive, if you look at it carefully, has a special block associated to parity. So in this example, it's logically broken down into 4 drives of data. But in order to have this parity, which is used to rebuild the block, it has to take parity and spread them out amongst the drives as well. I won't go into all of the following block by block. You could probably figure that out. You can follow it along. You actually have a total, not of the 16 blocks you see laid out here. We only have, in terms of actual data, we only have 12. The other 4 blocks, which is spread amongst the 4 drives, is used for parity only. It needs to do that. If one drive drops off, it needs that to rebuild the missing drive. And it does it on the fly until the drive has been replaced, which slows it down because it has to do these calculations on almost every read or write. But once you've put the other drive in and it's rebuilt, then it will go back to its full speed. And the full speed on this is, as you'll see later, I break them out. You have a little bit of performance improvement, but not a lot, mainly because of the extra calculations you have to do. But look at the result. We have 4 1 terabyte drives, and we wind up with the result of 3 terabytes of actual storage space. Then we have RAID 10. Now RAID 10 is an unusual one, but it provides the best of both worlds. But it's costly in terms of the number of disk drives that it needs. So we have pairs. We have a RAID 1 taking place between disk drives 1 and 2, and another RAID 1 between drives 3 and drives 4, and then the combination of them become a RAID 0 or full mirroring. And if you follow the blocks like we did before, you will see that there is some alternating between them so that we have the benefits of performance of a RAID 0. So this will run as fast as a RAID 0. However, it also uses up as much drive space, in this case number of drives, as a RAID 1 would use. Basically, you have to use 2 for 1. The result, as you can see here, even though we have 4 1 terabyte drives, the output is only 2 terabytes in total. Now let's talk about the interfaces that you need to use. I've already mentioned one of them, which is a dedicated hardware interface. That is one way. This is a PCI card you can buy from Amazon and put in your computer. This particular one, I believe, has 2, 4, 6, 8 ports on it. You connect up to 8 drives on it, and it can be configured to be any of the RAID configurations that we've discussed, the popular ones. The other way, which is probably the simplest way for most people, but it also is the least performing of them all, but you can actually use Windows 10 to do one particular type of RAID, which is the drive striping, or RAID 0. It can do that totally in software within Windows. It's automatically provided in Windows 10. And then the third option is the way I did it in the last video. Most new motherboards come with BIOS options to this. What runs on the BIOS is not hardware, it's not software. When we say hardware, that usually means that there's actual logic chip on the card that are dedicated to switching things very rapidly. Whereas software, is a program you could load and overwrite. Even if it's a driver, it still can be overwritten very easily. Well, the BIOS, it's not trivial to configure those things, but when it does run, it sort of fills the gap between these two. And it'll perform probably a little closer to the software version of it, nowhere near what the hardware one would do for you. So it sort of sits in the middle. Now let's look at the data paths, just to get an idea. This is getting a little bit in the weeds, but it might be helpful to some of you. For example, if you took a regular non-rated single disk drive, how does it work? Well, it uses a SATA connector, which is only 5 wires, 2 for transmit, 2 for receive, and 1 for ground. So with those, you're going into a SATA controller. The SATA controller then converts that into a full 16 or possibly 32 line parallel port directly to the central processing unit. But they're very fast, SATA, because the transmission and reception rate here is quite fast. Much faster than most disk spindles can ever spin, so you don't really lose that much. At least with what we call SATA 3 or SATA version 3. Now, let's look at RAID 0. With RAID 0, you have 2 separate ports going into hardware controller. It has a separate port for each of its drives. It then does the conversion directly that goes to the SATA controller, and it's able to bypass the conversion of the serial to parallel, and it talks to it, bypassing most of the logic on the SATA controller until it gets ultimately to the central processing unit. Okay, now RAID 0, but using motherboard BIOS, this is how the data path will flow. We have the 2 drives going into a RAID controller. In this case, the RAID controller is the motherboard itself, or at least some logic that's on the motherboard directly dedicated to providing RAID capability. Then it's obviously controlled and configured by the BIOS firmware. That's the hardened software that's dedicated on the motherboard itself. Then from there, it goes to the SATA controller. So the RAID controller that's built onto the motherboard actually converts into its serial to parallel converter. But in addition to this, it doesn't only go directly to the central processing unit and then be good from that point. It has to have a small driver piece of software also in the operating system in order to put some pieces together and make sure that this works properly. That's what slows it down from a hardware implementation. Well, also, the BIOS firmware itself is really a software implementation. In the case of using RAID 0 with the operating system software only, well, now you really don't have the motherboard helping you on this. The drives go through the normal SATA controller, and they get converted to parallel directly to the central processing unit. But now you need a very large piece of operating system software. A couple of different drivers have to be added in order for that to work properly. Windows does it automatically when you choose that option. Because it's running more within the operating system, will actually run a lot slower overall. So those are all the different data path options. Now let's talk about performance and how RAID affects that. Well, the performance of a RAID configuration can, as I've mentioned already, can either decrease performance, and it does in some cases, or it can increase performance. Definitely does that, especially RAID 0. Or it can have little or no effect on performance, sort of what takes place with a RAID 5 and RAID 6 and a couple of other ones like that. Now, what determines whether or not it's going to affect performance or not? Well, that is primarily what physical method is used. Is it using, as I said already, hardware, firmware, or software? Each one of those will have a different impact on it. The type of configuration, as I've gone through in great detail. Is it a RAID 1, 0, RAID 5, or whatever? And then another factor which most people don't realize when you're using RAID is how full these disks are. If it's a very large percentage, normally when you get about 3/4 full, definitely by the time you get 80, 85% full, you start finding that the system slows down. This is especially true with configurations like RAID 5 because it has to do much more calculation and create and shuffle information around a lot more as the disks are filled. So just keep that in mind. Now let's show the performance characteristics very quickly. For example, RAID 0, it can really improve performance as I showed in my last video. As you add each additional drive, it increases the performance, but it's not linear. This curve here, which I'll expand for you, shows that, for example, if you add in 5 drives, you're going to get the equivalent of about just over 4 drives performance as if they were running singularly. If you add in 9 drives, you're going to get just over 6 drives of performance. So you can calculate the formula on that if you're interested. But RAID 1 tends to be a slight to negligible performance hit. The write operations are slowed down because it has to duplicate between the 2 disks. But the read operations, you wouldn't even notice a difference if you ran performance tests on it. RAID 5, similar one. Very slight performance reduction, about the same as, and it comes out to be the same, unlike the RAID 1, of whether or not you're doing a read or a write operation. But after a drive failure, and you're in the replacement mode, what they refer to as the limp mode, the configuration will take a long time to recover. This will take probably about as long as 3 or 4 times longer than the recovery of RAID 1, which is pure mirroring. And then of course there's RAID 10. Because of the layout of RAID 10 and the fact that you're spending an awful lot of drives taking care of that, you will generally see no performance costs associated with it because you're actually using half the drives to account for not only parallelism but also redundancy of the data and performance as well. So that by far, if you really have an enterprise-wide system, RAID 10 is where they're going these days, a very large organizational RAID configuration. You can get improved redundancy. As I mentioned already, RAID 0 has no redundancy whatsoever. You're completely expanding the disk out with the space. There's no copying of the data amongst the drives, and it actually reduces some of the redundancy factor. The more drives you put in, you're multiplying the failure point. So it actually can lower it down, but that becomes a case whether or not you're using high quality drives or not as well. RAID 1, there's 100% improvement in redundancy. There's no way you're going to lose that data unless it dies a second time while it's trying to recover. So if one of the 2 drives die, assuming you have a 2-drive configuration, you take the bad one out, and they usually are hot swappable. You put a new one in, it automatically, in most cases, at least with most hardware controllers, it'll automatically start replicating over again to catch the other drive up. If it were to die again during that operation, well, then you could lose data. And that's also where RAID 10 comes in, because RAID 10 is actually counts for that with another RAID configuration. And of course, RAID 5 and RAID 10, it improves the redundancy considerable, much more over what RAID 0 has, but not necessarily as good as RAID 1. Well, it all depends. Well, you can actually drop multiple drives if you have RAID 10, for example. Now, how about increased data loss, the risk of that? Well, as I said before, RAID 0 has a very high risk. Fortunately, if you go with a high performance drive or a high quality drive, especially a solid state drive, you pretty much mitigate most of that risk because those are not the same kind of failure rate that a spinning drive would have. So the risk actually goes down low if you go to a solid state. That's why in my last video, I would not have done that if that was 2 hard drives doing a RAID 0. I only felt comfortable doing that if it's a RAID using solid state drives. And then RAID 1, the risk of any data loss is limited to the risk of the failure in the hardware itself or the SSD controller or the operating system. Any of those can cause RAID 1 data loss because those are factors pretty much out of the control of the actual drives themselves. The drives can be functioning perfectly well, but if any of those other 3 things fail, you could lose data, especially if it's in the middle of a write operation. And then RAID 5 or RAID 10, the risk of significant data loss is very low. That's because you have it spread out amongst many more drives. But it's still possible, again, during a write operation that goes bad in most cases. Now let me talk about another method that is not really RAID, but it's similar to it. And it's a factor that's built into another whole file system called ZFS. Now there is this thing called a backronym. They actually turned ZFS into an acronym and they gave it some names. They called it the Zettabyte file system. And it was originally created by Sun Microsystems for their advanced Solaris workstations. I use those. They're really good. It eventually went public domain after it went through, I believe, Oracle. It has some very good features to it. For example, it can do very efficient compression. It can do snapshots, so we can see just the changes that took place from one major set of operations to another. It can do continuous integrity checking. It's constantly checking and verifying the error correcting codes that it has to make sure that they're still valid. And it shuffles things around when the disk is idle to make it most efficient and speed up performance as well. It's integrated with something called RAID Z. It's a form of RAID. Not all the ones we just talked about, but some of them. And it also has what we call access control lists, ACLs, a very robust set of security. How do you set the security on your files? Now, what are the RAID Z modes? There are a few. The main four that you'll find are RAID Z0, RAID Z1, RAID Z2, and RAID Z3, and they're all similar, although more robust and definitely handle error correction better than the equivalent of the RAIDs that I've listed there. For example, RAID Z0 is very similar to RAID 0. There is no redundancy, but it does have fast performance. It does have auto repair partially. Doesn't necessarily account for something that's major, but if it starts seeing a weak spot on the disk, it'll compensate for that. Then RAID Z1 is similar to RAID 5, and that's what I'm going to have in my new server. And it allows one disk failure. So I have 4 disks in there. I could drop one, and it'll keep on cooking. And with ZFS, it won't take the same performance hit that regular RAID 5 would take. And then there's RAID Z2, which is similar to RAID 6. It allows up to 2 drives being dropped. And then finally, a less frequently used one is RAID Z3. And it's based upon a combination of RAID 7 and RAID 1. RAID 7 was one of the oddball ones I mentioned earlier. And it allows you to lose up to 3 disks or, depending on the configuration, all but one. As long as you have 1 disk left, let's say you have 3 disks, you lose one, it's rebuilding, and then it loses another one. Well, the RAID Z3 can recover from that. But again, you have a cost, just like we had in the regular RAID ones. That will cost you 2 drives of space. The conclusions, well, the use of RAID technology is not for everyone. It's quite complicated. It's hard to set up, and it's confusing to see what happens when there's a failure of a disk. But if you do your homework on it, you understand how it works, it can be very, very handy. I use it. I will continue to use it, especially in my servers. The hardware and software needed to properly use RAID is not trivial. In most cases, it's driven by your choice of the hardware and software that you want to do. Obviously, pick Windows, just do regular striping. That's very simple to set up. I didn't even cover that in my last video because it's pretty straightforward. If you want to get something more sophisticated, then you might want to have more sophisticated software, like using the ZFS file systems. And finally, you can obtain vast improvements in redundancy and/or performance. And that depends on the configuration you've chosen and the number of drives you've dedicated to it. However, you may also increase the risk, and sometimes significantly, of total data loss. RAID is not a replacement for backups. RAID is redundancy. It allows you to have duplication and recreation of data on the fly, not archival. If you were to corrupt a RAID because you put bad data out there, RAID doesn't help you with that. The corrupted data that you put out there is now going to be your data, whereas a backup allows you to go into an archive. You may mess up a file today, but if you have a backup that was taken of that exact same file a couple of days ago or even a week ago, then you can go to the backup, pull it back, and recover the thing that you did. Well, that went pretty well, I hope. Hopefully you learned something about RAID and how powerful it is when you have a personal computer and you have built into the system some features that allow you to do it. I mean, you can make systems faster, you could make them with more capacity, you could make them correct for errors. So there's a lot of capability with RAID, and hopefully you got that out of today's video. Once again, if you got something out of today that you found useful or enjoyed in any way, please subscribe to my channel. My head will pop up here in a second. Click on it and follow along. Subscribe to my channel. And once again, it doesn't cost anything to subscribe. Take care, and thank you for watching.